Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper trending on X, published on July 14th, 2025, just about 3 days ago. This paper reveals that NVIDIA's new Blackwell architecture is incredibly power efficient for low-precision tasks, with its new FP4 format consuming only 16.753 watts. The paper is titled, Dissecting the NVIDIA Blackwell Architecture with Microbenchmarks 2507.10789V1. And the findings paint a really interesting picture of the trade-offs between old and new GPU architectures. The authors developed custom microbenchmarks, which are small, targeted programs to uncover performance details that aren't publicly documented. Alright, so these first tables lay out the architectural differences between the new Blackwell chip and its predecessor, Hopper. We're comparing the consumer RTX 5080 against the data center H100. A key change is in the streaming multiprocessor, which is the core processing unit on the GPU. Blackwell uses unified units for different types of math, like FP32 and INT32, which represent numbers at different levels of precision. Hopper, on the other hand, keeps them separate. This comparison also highlights how Blackwell prioritizes new, lower precision formats, while Hopper retains strong support for high-precision FP64 calculations. Building on that idea of unified units, this next table really quantifies the performance impact. It measures latency, which is essentially the time delay for a single calculation measured in clock cycles. For pure INT32 or FP32 tasks, both chips are almost identical, but the real story is in the mixed workloads. Blackwell is about twice as fast, with a latency of around 16 cycles compared to Hopper's 31. This clearly shows the advantage of its unified design. Conversely, for high-precision FP64 math, Hopper is vastly superior, highlighting a deliberate design choice. Now, moving from latency to throughput, which is the rate at which the GPU completes calculations. This next chart plots performance as the number of instructions grows. You can see the performance lines for both the new Blackwell GB203 and the older Hopper GH100 are very close on standard INT32 and FP32 tasks. What's interesting is how Blackwell's throughput climbs more smoothly. This suggests its new warp scheduler, which manages how work is distributed, is more efficient at ramping up. However, Hopper still shows better overall throughput on those high-precision FP64 tasks. Okay, but performance isn't just about raw calculation speed. Memory plays a huge role too. This next chart looks at the memory hierarchy, which is the layered system of memory, from the fastest, smallest caches right next to the processor to the slower, larger main memory. The plot shows latency, the time to fetch data, as the amount of data gets bigger. You can see these steps in the lines. Each step up means the data no longer fits in a faster cache. Hopper's L2 cache is faster, but Blackwell's is larger, letting it handle bigger datasets. So we've seen the architectural differences in memory, but how does that play out in a real-world heavy-duty task? This table gives us a great case study. It shows the throughput for a dense general matrix multiplication, which is a core calculation for many AI models on both chips. Throughput here is measured in T-flop per second, or trillions of calculations per second, and the results are pretty stark. Hopper consistently outperforms Blackwell, often by a factor of 3 or 4. This suggests that for these large memory-intensive tasks, Hopper's superior memory bandwidth still gives it a decisive edge. So to wrap things up, this paper paints a clear picture of specialization. While the older Hopper architecture still excels at huge, memory-heavy training tasks, Blackwell is clearly optimized for a different world. It shines with its power efficiency and new low-precision formats, like FP4 and FP6. These formats use fewer bits to represent numbers, allowing for faster, more energy-efficient calculations. It's a classic engineering trade-off: raw power for some workloads versus lean efficiency for others, especially AI inference. That's all for this AI Research Roundup. Thanks for tuning in.